Hello and welcome to lecture 55 of the course Computational Complexity. In the past lecture, we saw the communication complexity model and we saw a bunch of examples and we defined what is called the protocol tree, right? And we saw a protocol for equality of 2-bit inputs, and we saw the illustration of that protocol in the protocol tree model. So now let us try to understand what is happening here. As we observed in the previous lecture, some leaves have correspond to multiple input pairs, right? So this particular no leaf has that is encircled with green color has 4 input pairs that reach here, whereas some other leaves like this yes leaf has only 1 input pair that reaches here. So which input pairs reach where and how are they divided, right? So one thing must be clear: any specific input pair it reaches only a specific leaf. It cannot go to 2 different leaves, right? Because each of these questions have are deterministic questions and have deterministic answers, right? So one specific input pair follows a certain path. It cannot go into 2 paths. That possibility is not there. Okay. So what we will do is to first see. So I already explained. I already saw a proof that deterministic communication complexity of equality is at most n+1, right? Which was the n+1 bound was the trivial bound, where Alice sends everything to Bob and Bob replies by 1, right? Which is applicable for any function. And now we will see that this bound is actually very close to being optimal, or in fact it is optimal. So we will see a proof that deterministic communication complexity of equality is actually at least n. Okay, so how will we see that? We will show that any protocol tree for equality has at least 2 power n leaves. So in this tree we have 4 leaves at the bottom here, and another set of 4 leaves in this red triangle, so that's 8, and then 2 leaves on the top, so 10 leaves. There are 10 leaves, and to build a tree with at least 10 leaves you need to have a tree of height at least 4. We need height at least 4. So 10 leaves means at least 4 height, so that gives you a bound on the height, a lower bound on the height, and which is the same as the lower bound on the communication complexity. Right. So we will show that the tree that, has at least 2 power n leaves if it computes equality. Okay. So consider any input pair where Alice and Bob get the same input. Let's say x and x. This is equal to 1. So the function has to return 1. Suppose Alice and Bob get x1 x1 and Alice and Bob get x1 x1. That is one possibility, and Alice and Bob get both x2 x2, right? The claim is that these 2 input pairs x1 x1 and x2 x2, these 2 input pairs must go to 2 different leaves. So here in this picture, if you see that the green leaf here that has 4 combinations, 4 input pairs, but that was a no leaf. What we are saying here is that any yes input combination, any yes input pair must go to 2 different leaves, and we know that there are 2 power n possible binary strings of length n. So there are 2 power n possible yes input pairs. So starting from all 0 to all ones, where Alice has x like all 0 input, Bob has all 0 input. Let's say Alice has 0 0 0 0 1, Bob has 0 0 0 0 1, up to all the all ones input going to both Alice and Bob. So there are 2 power n input pairs which return yes or which return 1 as the correct answer. What the claim is that all of these 2 power n input pairs have to go to distinct leaves. None of these pairs can go to the same leaf. So that means that the tree has to have 2 power n leaves to accommodate these 2 power n yes input pairs. Okay. So because of which the height should be at least n. So let us see why that is the case. Suppose the pair x1, so suppose x1 and x2 are 2 distinct values. X1 and x2 are not the same value. So suppose x1 x1 and x2 x2, they end up at the same leaf. Okay. The claim is that if this happens, then the input pair x1 x2 also must go to the same leaf. But then that leaf answers yes, right? Because x1 x1, the answer is yes. Any leaf is a place where you output something. So the leaf answers yes. But then x1 x2 is two inputs, so it is not equal. They are not equal. We are computing the equality function, right? So when x1 comma x2, when it goes to yes leaf, that is an incorrect answer, right? So this red underlined part is a key observation. If x1 x1 and x2 x2 go to the same leaf, then x1 x2 must also go to the same leaf. But then that is not correct. So that means that each pair x1 x1 x2 x2, everything must go to distinct leaves, which means all the input pairs that answer yes must go to distinct leaves, which means there are at least 2 power n leaves, which means the height has to be at least n, right? So now let us try to see why x1 x1 and x2 x2 must go to the same leaf, or sorry, different leaves, right? In any protocol, right, that computes equality, so this whole thing is for equality. If x1 y1, okay, this particular claim is actually not for equality in any protocol computing any function. Okay, suppose if x1 y1, right, and x2 y2 go to the same leaf, right, it is possible that x1 y1 and x2 go to the same leaf, then the claim is that x1 y2 and x2 y1 also must go to the same leaf. So in other words, so you can think of some coordinate kind of setup. Let's say this is x1, this is x2, this is y1, and this is y2. So x1 y1 is this input, maybe I'll highlight with blue this input. x2 y2 is this input. So now if these two input pairs go to the same leaf, then it means that the other inputs x1 y2 and x2 y1 also must go to the same leaf. This is the claim. So all these 4 must go to the same leaf. If two diagonally opposite points go to the same leaf, then the other diagonal, the points in the other corners also must go to the same leaf. Why is this the case? Okay, so suppose x1 y1 and x2 y2 go to the same leaf, right? So let me draw a picture. Suppose x1 and y1 something. Okay, this is the leaf. This is the leaf well. Now suppose, now we want to show that x1 y2 also goes to the same leaf. Suppose not, x1 y2 diverges and goes somewhere else. Let us say this point that we have drawn from a dotted line, this is the point of divergence of x1 y2. x1 y2 diverges here. Okay, so why did x1 y2 diverge here? So till this point x1 y1, x2 y2 and x1 y2 travel together to reach this point. Let's say this point is V. At point V they diverged. Why did they diverge? So this means that, now what could have happened at this point? This means at this point whoever had responded, maybe Alice spoke or Bob spoke. Alice could, if let's say Alice is the one that spoke. So suppose Alice spoke, means Alice gave a different answer for x1 y2 from x1 y1 or x2 y2. So x1 y1 and x2 y2 go this way, go to the right, and x1 y2 goes to the left. So suppose Alice was speaking here at the vertex V. Now suppose Alice, so all that Alice knows is that she is at, or they are at V. Alice and Bob together are at V. If it was x1 y1, she would have gone to the right. Because it is x1 y2, she goes to the left. But then Alice does not know what is Bob's input, except for the fact that whatever was Bob's input, together with Alice's input, they managed to reach the point V. Apart from this, Alice has no other information on Bob's input. The only thing that she knows is that Bob's input made them reach the point V. So at this point, x1, y2 and x1, y1, these two scenarios, Alice does not have the power to distinguish, because all she knows is her input is x1 and that they are at the vertex V. She does not know she cannot distinguish x1, y1 and x1, y2. So it is not possible that Alice is the one speaking here. Now, so suppose Bob is the one speaking here. Now I can make the same argument with x1, y2 and x2, y2. Now Bob only knows that his input is y2 and that they are together at V. Whether Alice's input is x1 or x2 cannot be distinguished by Bob. So he cannot distinguish x2, y2 from x1, y2. x2, y2 and x1, y2. He cannot distinguish the two. So it is not possible for him, for Bob to be the one, Bob to be speaking here, because if Bob was speaking here, he cannot distinguish and he cannot give two different answers for the situation x1, y2 and x2, y2. So this means that there is no possibility that x1, y2 diverges from the path taken by x1, y1 and x2, y2. So if x1, y1 and x2, y2 go to the same location, x1, y2 must also go to the same location. And same thing applies for x2, y1. It's a very symmetric argument. Right? So that completes the claim, and that completes this proof that all the distinct pairs x1, 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 x2, x2, x3, x3, all the pairs that are yes input pairs must go to distinct leaves, because x1, x2 is not a yes input pair. But if x1, x1 and x2 go to the same leaf, then x1, x2 must also go to the same leaf. So this means that the height of the tree has to have 2 power n leaves, and that means the height has to be at least n, right? So this shows that the deterministic communication complexity of equality is at least n. Okay. So now let us see another function. Okay. This is called set disjointness. We are actually measuring whether two sets are disjoint or not. Okay. So we have already seen examples in the previous lecture where we have seen the correspondence between n bit vectors and subsets of 1, 2, 3 up to n, right? So let us say Alice has the input, maybe I write here, Alice has the input 1, 0, 1, 1, which corresponds to the set 1, 3, 4. Let us say Bob has the input 0, 0, 1, 0, which corresponds to the set containing just 3. And what we want to measure is whether these two sets are disjoint. Obviously this is not disjoint because both of them contain the element 3, right? So disjointness is 1 if the sets are disjoint, or in other words, in terms of bit positions, for all indices I, either Alice's xi should be 0 or Bob's input yi should be 0, and 0 otherwise meaning there should be some index j for which xi, xj and yj should both be 1. So in this case this is the third index. So suppose Bob's input was this, which corresponds to the set 2. Now this means that in all the indices one of the Alice's input or Bob's input is 0. So this is disjoint. So to put it very simply, if the sets corresponding to Alice's input and Bob's input are disjoint, then the output is 1. If the sets corresponding are not disjoint, the output is 0. And disjointness happens to be a fundamental or rather canonical kind of problem in the case of communication complexity. So there are multiple settings like randomized, deterministic, and with some public coins, private coins and so on. But in all of this, disjointness plays a key role in trying to understand the complexity of the model, right? So we'll see disjointness to some detail. So that's why it's important to I decided to state it in a very formal manner. And just like equality, the deterministic complexity of disjointness is also at least n. Okay, so we'll see the proof a bit later. Actually, maybe it's not no proof, maybe proof later. Okay, before that, I want to define an important notion called combinatorial rectangle. So this is coming from the understanding of what is happening in a protocol tree. Okay, so consider this function. X and y are n bit vectors, and f of x y is saying whether x and y together have at least 4 ones. So maybe f of x y, I'll just state it a bit differently. F of x y equal to 1, sorry, if and only if x and y together have at least 4 ones. So in this situation, or in any situation, we can define what is called the matrix of the function. Okay, so I'll call it, let's say, m subscript f. This is this is a 2 power n by 2 power n matrix, right? As you can see what is happening here. So where the rows are indexed by Alice's input x and the columns are indexed by Bob's input y, and the let us take the first entry here, this entry that I am encircling with the blue thing. So this is when this is a function value when Alice has 0 0 0 and Bob has 0 0 0. So together they have 0 1s. So obviously the function value is 0. Okay. Now consider this one over here that I am highlighting with yellow. This corresponds to the output when Alice input is 0 1 1 and Bob's input is also 0 1 1. So together they have 4 1s. So the answer, so f is also 1. That's why this entry has 1. And like that you can verify each and every entry of this matrix. So it is just a function value for when x and y are given as at the index. Okay. So now let us try to understand, let us try to see a protocol and understand what is happening in this protocol. So together Alice and Bob have to decide if they have 4 1s, at least 4 ones. Right. So let us say the first at the top level, Alice speaks. Okay. Alice says whether he has or she has, her input has 0 or 1 1. If so, she goes to the left side, or it has more than 1 1, so 2 or 3 ones. Right. So again, all of this is for the case when they have 3-bit inputs. Okay. Even though I said n here, let's say consider the case where they have 3-bit inputs. Even this matrix is for 3-bit inputs. So that's why it's an 8 by 8 matrix. So Alice says whether she has 0 or 1 1 or more than 1 1s, 2 or 3 ones. Now consider, let's look at the left side. If Alice has 0 or 1 1, now if Bob has 0, 1 or 2 ones, right, that means that the maximum number of ones they together have is 2 plus 1, which is 3. And in this case the function value will be 0 because function value is 1 only when they have 4 ones. So that is what I have indicated here at the leaf. The other case is when Bob has 3 ones, that is the branch, this branch over here. Why Bob has 3 ones? Now if Bob has 3 ones, then Alice has 0 or 1 1, Bob has 3 ones. So the function value really depends on whether Alice has 0 ones or 1 1. So and so we ask that question, and depending on that the function value is 0 or 1. And similarly you can trace the path on the right hand side. Alice has 2 or 3 ones, and then we subdivide into further case when Alice has 2 and Alice has 3 ones. Right. So again notice that Alice herself is speaking even after saying whether she has 2 or 3 ones. Right. and then depending on that, then Bob has to classify his input, whether together they have 4 or together they don't have 4, and basically one more response from Bob is enough. So together they compute the function, and this tree has depth 3, right? So depth of this tree is 3. So which means this function can be computed. The deterministic communication complexity of this function is at most 3, less than or equal to 3. Well, there could be a better algorithm, better protocol to compute this function, but we do not know. So let us try to understand what is happening. Maybe I'll just remove the highlights because that could be misleading to what I'm saying. Okay, so now consider this one that is outlined here with blue, right? This one. So when do we reach here? Which input pairs reach this leaf? The input pairs that reach this leaf are those where Alice has 2 or 3 ones, and then further refined by Alice having 2 ones, and then Bob has 2 or 3 ones. So Alice has 2 ones and Bob has 2 or 3 ones. Okay. So which is actually corresponding to the cells that are marked here by the same kind of blue outline, right? So the fourth row, 4th, 6th and 7th rows, and 4th, 6th, 7th and 8th columns, right? 4th, 6th and 7th row correspond to Alice having 2 ones. 4th, 6th, 7th and 8th row columns correspond to Bob having 2 or 3 ones. So exactly these entries that are outlined by the blue color are the ones that reach that leaf. Similarly, you can check this particular leaf here that is outlined with the light green here. Alice has 2 ones and Bob has 0 or 1, and those values correspond to exactly the cells that are outlined with the green color, where Alice has 2 ones and Bob has 0 or 1 ones. So the 4th, 6th and 7th row and 1st, 2nd and 4th columns, sorry, 1st, 2nd, 3rd and 5th columns of the matrix, 1st, 2nd, 3rd and 5th columns and 4th, 6th and 7th rows. So this is exactly marked with the green color. Similarly, this yellow highlighted the rightmost leaf happens when Alice has 3 ones and Bob has 1, 2 or 3 ones. So there is only one row corresponding to Alice having 3 ones, which is the last row, and all the columns except the first column correspond to 1, 2 or 3 ones for Bob. So that is exactly the set of highlighted entries in the last row. So what is it that you can notice here? All the entries that are like the green outlined ones reach a certain leaf, and all the entries that reach that leaf are give the output 0. Blue outlined ones, all the entries that reach that leaf give the output 1. All the entries that reach the yellow highlight give the output 1. So everything that reaches a certain leaf gives us fixed output. Another thing is that all these are kind of very there is a pattern here. So now suppose I swap the 4th and 5th columns, bringing the green parts together, and then maybe there is one more row here. If I swap the 4th and 5th rows as well, then all the green green outlined cells will be together as a rectangle, and the same thing will happen for the blue entries. So there is this notion of a combinatorial rectangle. Combinatorial rectangle is nothing but you are picking a certain number of rows and some columns, and you take the cross product of that, and that is what is happening with the blue outline, green outline and the yellow highlight here. And in fact, you can see that at every stage of the protocol and at every node in this protocol tree, not just the leaf, any node in this protocol tree, you are always at a combinatorial rectangle. Okay, so I will define it formally and then we'll go there. So a combinatorial rectangle in x cross y, x is Alice's input domain and y is Bob's input domain, is a subset that is equal to a cross b. So a combinatorial rectangle R is just a subset A cross B. So what I mean by that is, so this is not a combinatorial rectangle because it's not a of the form A cross B. If so A has to be this range and B will have to be this range, and A cross B will include this part also, this top corner also. So this is how a combinatorial rectangle should look. But then it need not be contiguous, meaning I could allow, let's say B was this itself, but A was in two pieces, this one and this one. So then the combinatorial rectangle would look like this and this. Or even B could be split. So let us say there is some part of B that is over here. So then these four parts together will form the combinatorial rectangle. There could be even more parts, but right. So all the green coming back to the original matrix, all the green outlined ones form a combinatorial rectangle, or the blue outlined ones also form a combinatorial rectangle, or the yellow highlighted ones also form a combinatorial rectangle. So it is just a subset of the form A cross B. Okay, and the key point here is that why did we define this? Is that we observed that all the leaves, all the entries that correspond to all the leaves are combinatorial rectangles. All the entries that correspond to a certain leaf are combinatorial rectangles. And not just that, all the entries correspond to leaves are all output the same value. So the green outlined entries all correspond to the 0 output. Blue outlined all correspond to the 1 output. And you can even go back and verify the earlier tree that we drew for equality. You can see that each the outputs corresponding to each leaf is a combinatorial rectangle. So let us try to understand why this happens. Okay. There is another definition of combinatorial rectangle. So a set R is a rectangle. Okay. So the before getting into that, one more point I want to say is that combinatorial rectangle need not be a contiguous one block rectangle. It could be something like multiple blocks also. So it could be something like this, as long as it is some cross product of A cross B. This also could be a combinatorial rectangle. So where A will be this domain, this domain, and B will be this domain. Right. Okay. So coming to the other definition, the other definition is that R is a rectangle if and only if whenever you take x1 y1 in R, which is this corner, and x2 y2 in R, the points that I am marking with blue color, that necessarily means that x1 y2 also must be in R. So this may seem very familiar to what we said above. Why is this true? So suppose it is a rectangle, in the sense that suppose it is of the form A cross B, then we know that if x1 y1 is in R, then x1 is in A, and x2 y2 is in R means y2 is in B. So A cross B means x1 y2 is also in R. To see the other direction, suppose x1 y1 in R and x2 y2 in R implies x1 y2 in R, right? Now consider the sets. Let's say, so then we have to show that R cannot be of something like this. It has to be a proper rectangle. So the answer is, consider the set of all A's, a set of all X's for which xy is in R. So maybe set of all X's for which xy is in R, and you call this A. Okay, so the projection onto the x domain, and similarly consider the projection onto the y domain and call it B. All the pairs, all the y is such that xy, there is some x for which xy is in R, and the claim is that A cross B, R will be equal to A cross B. Why is that? That's because consider a point, let's say we want to show that this L-shaped thing, R cannot be an L-shaped thing. So consider this point outside this. Now we know that there is, maybe I'll take it to a different color, or maybe green. There is this green point here that is in R, and there is another green point here that is also in R, right? Because otherwise, that's why this blue point was in A cross B. The x coordinate of blue point was in A because of some point, and similarly for the y coordinate. Now, because these green points are in the rectangle, and since we have the property that if x1, y1 and x2, y2 are in R, then x1, y2 is in R, this blue point also must be in R. So, like that we can fill this entire range as well. So, that means R also will be a rectangle. So, this means that this is another way to define a rectangle. If I have this property, then what I have, the shape that I have is a combinatorial rectangle. So, this is another way to define. So, a rectangle is either two ways to define. One is it is A cross B, where A is a subset of X, B is a subset of Y, or it is any set that has a property that if x1, y1 and x2, y2 are in R, that implies that x1, y2 is in R. Okay, and one point that I want to say here is that consider any protocol tree like this. Any node, every node here, every vertex in this tree corresponds to a combinatorial rectangle. So, in the beginning, if you notice, the root here corresponds to the entire matrix, and then we are dividing it based on whether x is 0 or 1 1 or x is 2 or 3 1s. So, then we divide it. So, 0 or 1 1 means it is either the first 3 and the fifth row will correspond to, it is just the first 3 and the fifth row go to the left, and the 4th, 6th, 7th and 8th row goes to the right, and but then this time the only the rows are divided, the columns, all the columns. So, it's something like this, something like this. This is what goes to the green part goes to the left hand side, and the red part goes to the right hand side. So, as you can see, even both the green and red are combinatorial rectangles. Okay. So, the claim is that in any protocol, every node is a combinatorial rectangle. And here you can see now we came to the green part, and y has 3 1s will correspond to, let us say, this sub part here. That is a further refinement. So, that is also a combinatorial rectangle. That is the left part, the right path from here. So, in any protocol, every node is a combinatorial rectangle. And further, all the leaves are all F monochromatic, meaning all the leaves have are places where the function value is the same. So, in a leaf, either the function value is all 0 or the function value is all 1. You cannot have one point of the leaf with fxy equal to 0 and another point of the leaf where fxy equal to 1 of the same leaf. And we have in fact seen the idea of the proof. So, we saw this proof earlier in the previous lecture. If x1 y1 and x2 y2 lead to any leaf, then x1 y2 and x2 y1 also must reach the same leaf. And in fact, this is true for any not necessarily leaf, any path, any node in the tree. So this means that any node in the tree corresponds to a combinatorial rectangle. So I have written it here anyway. Consider any node in the tree V and let RV be the set of inputs that reach V. Now the claim is that if x1 y1 and x2 y2 reach RV, then x1 y2 also must reach RV, which means RV must be a rectangle. Combinatorial rectangle. And since if V is a leaf, then V outputs the function value, right? So either the function value output at that leaf is 0 or 1. So it means all the entries at that reach there, which is RV, has to be 0 or 1. So which is what we call F monochromatic. Otherwise this protocol does not compute that F. So if there is a leaf at which some points correspond to 0 output, some points correspond to 1 outputs, that means you have to further go down. So that point is not a leaf. So all the leaves are F monochromatic, meaning evaluate to the same function F value. Okay, so any node in the tree is a combinatorial rectangle. So starting from so basically what happens is when you start, the root node is the entire matrix, and then every time Alice speaks, there is a subdivision of the rows. So it need not be just one cut; it could be like it could be a combinatorial cut, right? Like over here, the green was not just like one split, but then it's actually one split, but some rows go into one side, some rows go into the other side. And whenever Bob speaks, it's a vertical cut. So like that, every time it's split horizontally or vertically, but a rectangle when cut entirely, it remains a rectangle. That is the proof. Okay. So why are we doing all this? We are doing all this to get a technique to bound the communication complexity of any function. So suppose we know that a certain function has a certain matrix, and however which way you try to divide it into combinatorial rectangles, suppose that matrix requires it to divide into 1000 rectangles. That means that you cannot divide it into smaller number. You cannot divide it into 999 rectangles. Any way you try to divide, you need at least 1000 rectangles. Meaning, any protocol that you have for the function, right, must have at least 1000 leaves. So if it has 1000 leaves, the tree must be sufficiently deep. You should go up to log 1000 depth, which is log 1000 mod to the base 2 is at least 10 depth, right? So that is the statement here. If any partition of x cross y, the matrix f cross y, into f monochromatic rectangle requires at least t rectangles, then df is at least log t, right? So in fact I can say it is ceiling of log t, right, because you cannot have half bits of communication. So just to give an example, consider disjointness, right, that we said earlier. Disjointness, that is a function that indicates whether the two sets are disjoint or not. Consider disjointness. Now consider this set, maybe I'll just write it clearly. So we will show that disjointness must have some number of leaves. Okay. So now let us consider disjointness over 3 and consider this following: 0 0 0 1 1 1 0 0 1 1 1 0 0 1 0. Sorry. So what am I doing here? I am just trying to 1 0 1. I am writing all the strings x and the complement string. So these are sets, a certain set X and or a certain set A and their complement. Okay. Now the claim is that, so how many elements are there in this is called S. How many elements are there in S? S has 2 power n elements, because I take 2 power n possible strings X, and for each possible string X it is just one possible complement string. Yeah, I have written here already, S is of size 2 power n, right? And the claim is that each of these pairs must go to distinct leaves. You cannot have 2 of these pairs come to the same leaf. So basically, if X and Y are not equal, then X complement and Y complement cannot go to the same leaf. Why? Because either X intersection Y complement or Y intersection X complement is non-empty. It is disjointness function, right? So X intersection X complement is certainly empty, and Y intersection Y complement is empty. So So we know that disjointness of all the entries in all the entries in X is 1, right? So disjointness right, all the entries in S are 1. But if you take 2 distinct entries of X complement and Y complement, either X and Y complement intersect or Y and X complement intersect, which means that either disjointness of X and Y complement equal to 0 or disjointness of X complement and Y equal to 0. So now you can see why they cannot go to the same leaf. If X complement and Y complement go to the same leaf, then XY complement and X complement Y also must go to the same leaf. But then we know that X complement and Y complement are 1 entries, right? As I have drawn here, X complement is 1, Y complement is 1. But we know that at least one of the other entries, XY complement or X complement Y, one of them must be 0. So they cannot be part of the same monochromatic rectangle. So which means that all the elements of S must be in separate rectangles. So that means we have 2 power n different entries, all of which must be in separate rectangles. Which means the tree must have at least 2 power n leaves. Which means the height of the tree must be at least n. Right? So the disjointness of the deterministic complexity of disjointness must be at least n. So what we did here is to demonstrate a set such that all the entries of that set must be in distinct leaves. And this kind of a set is called fooling set, and this kind of an argument is called a fooling set argument. So we will see some more examples in the next lecture. So S has some certain size and all of S must go to different leaves. So that says that there has to be at least this many leaves for the protocol tree, so the protocol tree has to have at least this much height, which means the deterministic communication complexity is at least this much. So this particular claim, just try to think of it. If X complement and Y complement are distinct elements of X, why must it be the case that X and Y complement intersect, or X complement and Y intersect? Think about this. So I should write Y and X complement here, right? So at least one of them must intersect. Just think about it. If X and Y are of different sizes, then you can see that at least one of them must intersect because of the sizes. But if they are of the same size also, you can make a different argument. Just think over it. Okay. So what we have seen in this lecture, just to summarize, we saw the protocol tree in the previous lecture. We saw this notion that if x1 x1 and x2 x2 go to the same leaf, then or same node, then x1 x2 also must go to the same node, and that led to the definition of what we call combinatorial rectangles. Combinatorial rectangles are just A cross B, where A is subset of X and B is subset of Y. Or we had the other definition where it's a set, any set where x1 y1 and x2 y2 being in the set implies x1 y2 being in the set. Okay, so both of them are equivalent definitions. If you have one, you have the other. And we use that to show that show the following theorem, that if any partition of, and we saw that in any protocol tree every node is a combinatorial rectangle, and further all the leaves are F monochromatic combinatorial rectangles. F monochromatic means in those rectangles the F values are all zeros or all ones. So consequently, given a function, look at the matrix. What is the smallest number of ways in which you can divide the matrix into monochromatic rectangles? What is the smallest number of ways you can divide the matrix into monochromatic rectangles? Suppose it is T, then any protocol must take at least log T, must send at least log T bits of communication. Right? Again, it is exactly the same argument as what we saw. And disjointness, we saw that example of disjointness. We saw that we showed that it showed a set of size 2 power n, and we said that any partitioning into monochromatic rectangles must have at least 2 power n rectangles. This implies that disjointness has complexity at least log of 2 power n, which is n. So that's all that we saw in this lecture. We saw the main thing being the definition of combinatorial rectangle. And with that, I think I will conclude this lecture. And in the next lecture, we will see maybe few more techniques for lower bounding the communication complexity. After which we will, in subsequent lectures, we will see one application on circuit lower bounds. Thank you.